night, if the sky above you is dark enough, you can see another galaxy with your own eyes. Andromeda sits there quietly, a faint oval of light, 2.5 million light years away. It is not alone. Our galaxy has more than 50 companions, some of them close enough to be slowly torn apart. We live in a crowded neighborhood, surrounded by neighbors, wrapped in a family of galaxies that has been together since the beginning. Now imagine a galaxy for which none of that is true. Imagine a spiral of 100 billion stars turning slowly in the dark with nothing around it. No companions, no neighbors, no faint smudges of light in its night sky at all. The nearest other galaxy is so far away that it would be invisible to any telescope its inhabitants might build for a very long time. Just its own stars, and then blackness in every direction for hundreds of millions of light years. Such galaxies exist. We have photographed them. They sit in enormous, almost perfectly empty regions of space that astronomers call voids. And the largest voids are so vast and so empty that a civilization born inside one might conclude that its galaxy was the entire universe. Tonight, we travel to the emptiest places in creation. And we ask a strange question: whether being alone out there is a tragedy or a kind of peace. If you find comfort in the quiet, distant corners of the universe, consider subscribing to the channel. Let the deep stillness of empty space carry your mind somewhere restful as we drift together tonight. Welcome aboard, astronaut. Tonight, we drift through the cosmos. We rise away from Earth, past the moon, past the outer planets, and out of the flat, glowing disk of the Milky Way. And then we keep going until our whole galaxy becomes a small spiral of light behind us. From here, something becomes visible that no one on the ground could ever see. Galaxies are not scattered randomly through space. They are arranged. Threads of them stretch across hundreds of millions of light years, meeting at bright knots where thousands crowd together. Between the threads lie enormous dark spaces, almost entirely empty. The universe, seen from far enough away, looks like a web, or a sponge, or a network of roots reaching through the dark. Tonight, we will learn how that structure came to exist and why it looks the way it does. We will travel into a hole in the universe 300 million light years wide, where thousands of galaxies should be and only a handful are. We will meet the specific galaxies that astronomers describe as the loneliest ones we know. We will find out where our own Milky Way sits in this architecture and discover that something enormous and invisible is pushing us. And we will learn how isolation changes a galaxy, slowing its life, preserving its gas, keeping it young. Settle in. Let your shoulders drop. We are heading somewhere very quiet. Let us begin with the shape of everything. For most of the 20th century, astronomers assumed galaxies were sprinkled more or less evenly through space. There was no reason to think otherwise, and the surveys were too small to reveal anything else. Then, in the 1970s and 80s, astronomers began measuring distances to thousands of galaxies at once and plotting them in 3 dimensions. What emerged from those maps astonished everyone. The galaxies were not evenly spread at all. They were strung along filaments, long, thin chains of galaxies, stretching for hundreds of millions of light years. The filaments joined at dense nodes where great clusters of thousands of galaxies sat. Sheets of galaxies spread between filaments like enormous curved walls. And in between, there was nothing. Vast, round, dark spaces with almost no galaxies at all. One early map produced a pattern that looked so much like a human figure that astronomers nicknamed it the Stick Man. Later, surveys mapped millions of galaxies and confirmed the same architecture everywhere they looked. We call it the cosmic web, and it is the largest structure in existence. Nothing bigger has ever been found, and current physics suggests nothing bigger can exist. Here's the part that matters for tonight. In this architecture, the voids are not gaps in the picture, they are most of the picture. Roughly 80% of the volume of the universe is void. Emptiness is not the exception out here, it is the default. But what happens when we ask how anyone could possibly map such a thing? A photograph of the sky is flat. Two galaxies that appear side by side may be neighbors, or one may be 10 times further away than the other. To find the cosmic web, astronomers needed the third dimension, and getting it is slow, patient work. The method relies on expansion. Space itself is stretching, so distant galaxies recede from us, and their light is shifted toward the red end of the spectrum. The further away a galaxy is, the faster it recedes, and the greater that shift. Measure the shift, and you have the distance. But this requires spreading each galaxy's light into a spectrum, which demands far more light than simply photographing it. In the early surveys, astronomers measured galaxies one at a time, night after night, for years, to assemble maps of a few thousand. Modern instruments changed the scale completely. Today, a single telescope can capture thousands of spectra simultaneously, using fiber optic cables positioned precisely across the focal plane. Recent surveys have mapped tens of millions of galaxies in 3 dimensions. There is one strange artifact worth knowing about. Galaxies in dense clusters move rapidly in random directions, and those motions add extra shift on top of the expansion. In the resulting maps, clusters appear stretched into long, thin spikes pointing directly at us. They are not real. They are an illusion created by the measurement itself, and astronomers name them fingers of God. Once you know to correct for them, the true structure emerges. Filaments, walls, clusters, and between them, the great dark hollows we are traveling toward tonight. Now, let's go deeper into how such a structure came to be. The early universe was almost perfectly smooth. Almost. When we map the oldest light in the sky, we find tiny variations in temperature and density, differences of about 1 part in 100,000. Some regions were a fraction more crowded than average. Some were a fraction emptier. These were the frozen remains of waves rippling through the hot early cosmos before it cooled enough to become transparent. That is all gravity needed. A region slightly denser than its surroundings pulls a little harder. It attracts more matter, becomes denser still, and pulls harder again. Meanwhile, a region slightly emptier than average has weaker gravity, so its matter drifts away toward the denser regions nearby, leaving it emptier still. Over billions of years, that gentle imbalance amplifies without limit. Matter drains steadily out of the empty regions and piles up along the edges. The slightly crowded places become filaments and clusters. The slightly empty places become vast hollow bubbles, computer simulations that begin with nothing but those tiny early ripples and then simply let gravity run for 13 billion years, produce a cosmic web that looks strikingly like the real one. Same filaments, same walls, same enormous voids. It is one of the great confirmations in cosmology. The structure of everything, all the way up to the largest scales we can measure, grew from variations smaller than one part in 100,000. The voids were not carved out. They simply lost very slowly to their neighbors. But what happens when we go inside one? Let us travel to the constellation of Boötes and to a region roughly 700 million light-years away. In 1981, a team of astronomers mapping galaxy distances found something they initially assumed was an error. Across an enormous stretch of sky, the galaxies simply stopped. They checked the equipment, they checked the analysis. The gap was real. They had discovered a void about 300 million light-years across. Even now, it remains one of the largest known. To understand how empty that is, consider what should be there. Based on the average density of galaxies in the universe, a volume that size ought to contain around 2,000 of them. Careful searches have turned up roughly 60. Astronomers named it the Boötes Void, though it is more commonly known by a simpler name, the Great Nothing. And the emptiness is not a matter of things being faint or hidden. Deep searches have looked repeatedly with increasingly sensitive instruments. The galaxies are not there. Almost everything that should exist in that volume is simply absent, drained away over billions of years into the surrounding walls and filaments. If you could travel to the middle of it, you would find yourself in a darkness unlike anything near Earth. In every direction, for 150 million light-years, essentially nothing. A hole in the universe, big enough to hold every galaxy you have ever heard of, and holding almost none of them. Now, let's go deeper, because the word empty needs qualifying. Voids are not vacuums. They are underdense regions, which is a different thing. A typical void interior holds perhaps 10 to 20% of the average density of the universe. Most of that is dark matter, spread thin and smooth, invisible except through its gravity. Some of it is ordinary matter in the form of extremely diffuse, warm hydrogen, far too sparse and too faint to form stars or to glow in any way we can easily detect. So the material is there. It's simply never gathered into anything. That distinction matters, because it explains why voids are not perfectly featureless. Simulations show that void interiors contain their own delicate internal structure, faint tendrils of dark matter, thin walls, and small hollows within hollows. The cosmic web repeats itself on smaller scales inside the emptiness, like a pattern that continues no matter how far you zoom in. And along those faint internal tendrils, small galaxies do form. Void dwarfs, dim and scattered, strung along filaments so tenuous that they contain almost nothing else. There is even an unresolved puzzle here. Simulations of how structure forms tend to predict more small galaxies inside voids than surveys actually find. Whether that gap comes from those dwarfs being too faint to detect, or from something incomplete in our understanding of how small galaxies form, remains genuinely open. The emptiest places in the universe still have questions in them. But that's not all, because these hollows have turned out to be unexpectedly useful. Dense regions are complicated. Gas is heated, stripped, and blown around. black holes erupt. Stars form in bursts. Untangling gravity from all that messy activity is genuinely hard. Voids are the opposite. Almost nothing happens in them, which makes them remarkably clean places to test the behavior of gravity itself. Cosmologists now use voids deliberately. Light passing through a void is bent very slightly outward rather than inward. And by measuring that gentle defocusing across thousands of voids at once, we can weigh the material inside them. Voids also leave a faint fingerprint on the oldest light in the sky. A photon crossing an expanding void loses a small amount of energy on the way through, arriving very slightly cooler than average. The effect is tiny, but stacking many thousands of voids together makes it measurable, and it provides independent evidence that the expansion of the universe is accelerating. The emptiest regions in existence, containing almost nothing worth looking at, have quietly become one of our better instruments for studying everything else. And yet, there's more to this story, because the truly haunting part is what it would mean to live there. One astronomer put it in a way that has been quoted ever since. If the Milky Way had been located near the center of the Boötes void, we would not have known that other galaxies existed until the 1960s. Think carefully about what that means. For all of human history, our understanding of the universe has been shaped by the fact that we can see other galaxies. Andromeda is visible to the naked eye from a dark side. Even a small telescope reveals dozens of others. The great debate about whether those faint smudges were nearby clouds or distant island universes was settled a century ago, precisely because our neighbors are close enough to study. In a void, none of that would be available. Astronomers there would build telescopes and see only stars, their own stars belonging to their own galaxy. Beyond that, blackness. They would have no reason to imagine anything else existed. Their cosmology would describe one island of stars in an infinite void, and every observation they could make would agree with it. They would not be wrong through carelessness. They would be wrong because the evidence was too far away to reach them. It is a genuinely unsettling thought, astronaut. Somewhere in this universe, there may be minds that have looked up for their entire history and concluded quite reasonably that they are all there is. The journey continues to the galaxies themselves. In 2016, a space telescope released an image of a modest barred spiral galaxy, seen roughly face-on, its arms wound loosely around a bright core. It is not spectacular to look at. What made it remarkable was everything around it. The galaxy sits deep inside a void. Its nearest significant neighbors lie so far away that they play no meaningful part in its existence. It has no companions being pulled apart, no larger galaxy to eventually fall into, no group, no cluster, no family. Astronomers described it at the time as one of the loneliest galaxies known. The image itself carries the point better than any description. In photographs of most galaxies, the background is scattered with others. Small, faint, distant, but present. Look closely at almost any deep image and you will find dozens of them. Around this one, the frame is unusually bare. There are other candidates for the title. Another spiral, much closer to us, sits at the edge of the local void and was nicknamed the Lost in Space Galaxy for the same reason. Various surveys have cataloged thousands of isolated systems with no significant neighbor within many millions of light years. But this one has become the image people remember, a single quiet spiral turning in the dark, with nothing nearby and nothing coming. Now, let's go deeper, because loneliness turns out to be surprisingly difficult to define. What exactly makes a galaxy isolated? You might say it has no neighbors within some distance, but which distance? 10 million light-years excludes almost nothing. 100 million excludes almost everything. You might measure by influence instead, asking whether any other galaxy has meaningfully affected it. That is more meaningful and much harder to determine, because gravitational effects fade gradually, rather than stopping at a line. You might ask about history. A galaxy might be isolated today but have merged with several others long ago, which would leave clear traces in the motions of its stars. Astronomers running large isolation surveys generally combine several tests. They require no comparable galaxy within a set radius, no evidence of recent interaction in the shape of the disk, and no disturbance in the distribution of gas. Galaxies that pass every test are rare. Most galaxies in the universe live in groups. Ours certainly does. And there is one more complication, which is that we can only measure what we can see. A galaxy might have a faint dwarf companion too dim to detect at that distance. Absolute isolation can never be proven, only supported. So, when astronomers call something the loneliest galaxy, they are speaking carefully. It means the loneliest we have found by the measures we can apply, with the instruments we currently have. But what happens when we look at our own address in all this? The Milky Way is not lonely, not remotely. We belong to the local group, a family of more than 50 galaxies bound together by gravity, dominated by ourselves and Andromeda. Several small companions orbit us right now, and at least one is being visibly shredded. The local group sits at the edge of a larger structure. Our group is part of a flow of galaxies streaming toward a distant concentration of mass, and mapping those flows revealed something remarkable in 2014. Astronomers traced the motions of thousands of galaxies and found that we belong to an enormous connected region, roughly 500 million light-years across, containing something like 100,000 galaxies. They named it Laniakea, from words meaning immeasurable heaven. It is not a cluster in the traditional sense. It is defined by motion, by the fact that everything within it is drifting toward the same gravitational focus, a region long known as the Great Attractor. So our position is thoroughly social. We sit inside a group, inside a filament, inside a vast flow of galaxies, all moving together. And yet, right beside us, sharing a border with our own local group, lies one of the emptiest regions in this part of the universe. And yet, there's more to this story, because we live on the shore of a void. It is called simply the local void. It begins immediately next to the local group and extends outward for well over 100 million light-years. It is not the largest void known, but it is by far the nearest. Our galaxy sits on its edge. We are, in a sense, standing at the coastline of a great emptiness, looking out, and the void is doing something to us. When astronomers carefully measured the motion of the local group after subtracting the expansion of the universe, they found we are moving at hundreds of kilometers per second in a particular direction. For decades, this was explained purely as attraction. The Great Attractor, and beyond it, an even larger concentration of galaxies pulling us toward them. Then, in 2017, researchers mapping the flows in 3 dimensions found that attraction was only half the explanation. An underdense region on the opposite side of the sky is effectively pushing us away. This is not a new force. Emptiness cannot push. But relative to the average density of the universe, a large void behaves exactly as though it repels, because everything around it pulls harder. Researchers named this region the dipolar repeller, so we are being drawn toward a great concentration in front of us and pushed by a great emptiness behind us, and both effects are roughly equal. The Milky Way is quietly fleeing the void it grew up beside. And yet, there's more to this story, because there is a genuine possibility that we ourselves live inside one, not a void like Bota's, something shallower and far larger. In 2013, astronomers counting galaxies out to great distances noticed that our surroundings appear thinner than they should be. Within a region roughly 2 billion light-years across, centered close to us, the density of galaxies seems to sit meaningfully below the cosmic average. If that measurement is right, our entire neighborhood, the local group, Laniakea, and a great deal beyond, sits inside an enormous, shallow underdensity. This is not a settled result. Counting galaxies across such distances is extremely difficult, and different teams using different methods disagree. But the possibility is being taken seriously, because it might help with one of the most stubborn problems in modern cosmology. When astronomers measure how fast the universe is expanding using nearby objects, they get one number. When they calculate the expansion rate from the oldest light in the sky, they get a slightly smaller one. The two disagree by more than the uncertainties allow, and nobody has resolved it. A local underdensity could contribute to that mismatch. Matter in the surrounding denser regions would pull our neighborhood gently outward, making nearby expansion appear slightly faster than the true cosmic average. Whether this fully explains the discrepancy is doubtful, and most cosmologists expect the real answer lies elsewhere. But it raises a quietly unsettling idea. We may not be observing the universe from a typical location. We may be measuring everything from inside a hole and not have noticed. The journey continues, and now we ask what isolation actually does to a galaxy. To answer that, we first have to look at the opposite extreme. Consider a galaxy living in a dense cluster, surrounded by thousands of others. That environment is hostile in ways that are easy to overlook. The space between cluster galaxies is not empty. It is filled with extremely hot, thin gas, heated to tens of millions of degrees by the cluster's gravity. When a spiral galaxy falls into a cluster, it plows through that gas at thousands of kilometers per second. Its stars pass through untouched, because stars are tiny and far apart. But its own cold gas, spread thinly across the disk, feels the oncoming material like a wind. That wind strips the gas away. We can see it happening. Deep images of nearby clusters show spiral galaxies trailing long streamers of gas behind them, with bright knots of newly formed stars strung along the tails. Astronomers call them jellyfish galaxies, and the name fits perfectly. Once the gas is gone, the galaxy cannot make new stars. The bright blue ones it already has burn out within a few million years. What remains ages steadily toward red. Add repeated close encounters with neighbors, which distort the disk, and outright mergers, which destroy it entirely, and the pattern is clear. Crowded galaxies are older, redder, rounder, and quieter. The denser the neighborhood, the more thoroughly it has been processed. Now, let's go deeper into what happens when none of that ever occurs. A galaxy in the middle of a void keeps everything. There is no hot intergalactic wind to strip its gas because there is no cluster and no dense surrounding medium. There are no close encounters to warp its shape because there is nothing close enough to encounter. There are no mergers because nothing ever arrives. The result is measurable, and studies of void galaxies find the same pattern consistently. They are bluer than average, meaning they are still actively forming new stars. They hold proportionally more cold gas, sometimes far more, because nothing has taken it. Their disks tend to be neat and undisturbed, with regular spiral structure and no tidal distortion. They are on average smaller and lower in mass because they never grew by consuming anything. In short, they look like galaxies that were left alone and simply carried on. There is something almost tender in the data. These are galaxies that were never harassed, never stripped, never absorbed. They have been quietly turning gas into stars for billions of years at a slow, steady rate, and they still have plenty left. The crowded galaxies burned bright and finished early. The lonely ones are still going. But what happens when we look at how far behind they are? Void galaxies appear to be running late because they grow only from their own gas, and only at whatever rate their internal processes allow. Their development has been slower than everything around them. In many respects, they resemble what ordinary galaxies looked like billions of years ago. The most striking examples are certain isolated dwarf galaxies found in nearby voids. One in particular has become well known among astronomers. It is small, irregular, actively forming stars, and remarkably poor in heavy elements. That last point is the significant one. Every element heavier than helium was manufactured inside stars. So the proportion of heavy elements in a galaxy is effectively a record of how many generations of stars have already lived and died there. This dwarf has one of the lowest such proportions ever measured in the nearby universe. Chemically, it resembles a galaxy from the early cosmos, still near the beginning of its stellar history, yet it sits only about 40 million light-years away in our present-day universe. It is not a relic that failed to change. It is a galaxy that has been developing normally, just very slowly, undisturbed, in a region where nothing ever comes to hurry it along. Isolation did not stop its clock. It simply let it run at its own pace. And yet, there's more to this story. So let us stand on a world inside one of these galaxies and look up. The night sky would begin the same way ours does. Stars in enormous numbers. A bright band across the sky where the galaxy's own disk is seen edge on. Star clusters, nebulae, the familiar furniture of a galaxy seen from inside. The difference would be everything beyond that. From Earth, a dark sky offers Andromeda to the naked eye, and a modest telescope reveals hundreds of galaxies. Point a large telescope at an apparently blank patch, and you find thousands receding into the distance, some of them nearly as old as time. From deep inside a large void, that entire layer of the sky is missing. There would be no nearby companion galaxies, nothing visible without instruments. And when astronomers there eventually built serious telescopes and pointed them at the dark, the results would come back nearly empty over and over for generations. Eventually, with sufficiently large instruments, they would find the distant walls of their void, a faint, remote shell of galaxies surrounding them on all sides, hundreds of millions of light years away. Imagine that discovery, learning that the universe is populated after all, and that everything else in it is impossibly far away, arranged in a distant ring around your solitary home. We looked up and found neighbors. They would look up and find a horizon. Now, let's go deeper into why these galaxies are so hard to study. You might expect the loneliest galaxies to be obvious. They are not. They are among the most difficult objects in extragalactic astronomy. The problem begins with distance. Voids are enormous, so a galaxy near the middle of one is typically very far from us, which makes it faint. The second problem is that void galaxies tend to be small. Isolation means no mergers, and no mergers means limited growth. Most void galaxies are dwarfs, and dwarfs are dim. The third problem is the most awkward. To confirm that a galaxy is isolated, you must demonstrate an absence. An absence is the hardest thing in observational science to establish. You cannot simply photograph a region and declare it empty. You must show that your search was sensitive enough to have detected neighbors if they existed. That means surveying enormous volumes of sky to a consistent depth, measuring distances to everything you find, and carefully accounting for what your instruments would have missed. This is why our catalog of truly isolated galaxies remains modest, and why the ones we know about tend to be the larger, brighter, easier examples. The loneliest galaxy in the universe is almost certainly not one we have named. It is more likely something small and faint, somewhere in the middle of a void we have not surveyed carefully, that no telescope has yet had reason to point at. But what happens to the voids over time? They grow. Matter continues to drain out of them. Any galaxy inside a void feels the gravity of the surrounding walls and filaments pulling outward in every direction. And over billions of years, that gentle outward tug moves things. Void interiors become progressively emptier, and void boundaries become progressively sharper. At the same time, the expansion of the universe is accelerating, and voids expand faster than the average. Their material is spread thin, so gravity resists the stretching less effectively there than in dense regions. The consequence is that the cosmic web is becoming more extreme with time. The dense parts grow denser and more tightly bound. The empty parts grow emptier and larger. The contrast sharpens, which means the loneliest galaxies are becoming lonelier and will continue to. Whatever faint neighbors they can currently detect on the distant walls of their void will drift further away, and their light will stretch and dim. Nothing dramatic marks this, no event, no boundary, no moment of separation. Only distance, quietly increasing across time scales that make our entire species look instantaneous. The universe is not tearing itself apart. It is doing something gentler and stranger. It is slowly spreading out and letting go. And yet, there's more to this story, because emptiness has an opposite, and it is worth seeing before we finish. If voids are where matter drained away, the walls are where it collected, and some of those walls are extraordinary. One of them mapped in the early 2000s, stretches for well over 1 billion light years, a vast sheet of galaxy clusters and filaments containing many thousands of galaxies, all strung together in a single connected structure. Others have been proposed that are larger still, and those claims are contested for an interesting reason. Cosmology rests on an assumption called the cosmological principle. It holds that on sufficiently large scales, the universe is uniform, that no region is fundamentally different from any other. Below a certain scale, structure exists. Above it, everything should average out into smoothness. That transition appears to happen somewhere around a few 100 million light years. Zoom out beyond that, and the filaments and voids blur into an even, featureless texture. So a structure spanning several billion light years is a problem. It should not be able to exist, because there has not been enough time since the beginning for gravity to organize matter on that scale. Some of these giant structures may turn out to be chance alignments rather than genuinely connected objects. Others may survive scrutiny and force adjustments to our models. It is a reminder worth carrying, astronaut. The architecture we have mapped tonight is real and well tested, but the largest scales of all remain unsettled, and the map still has edges we are arguing about. The journey continues one last time, and it is worth asking whether any of this is actually sad. We have used the word lonely all night because it is the word everyone reaches for, but it carries assumptions that a galaxy does not share. Consider what a crowded life actually involves out here. Galaxies in dense clusters are stripped of their gas by hot winds. They are distorted by encounters. They are torn apart and absorbed by larger neighbors. They stop forming stars and fade toward red. In the densest environments, most of them have already been processed into smooth, quiet gas-poor systems that will never make anything new again. Meanwhile, the void galaxy still has its gas. It still has its spiral arms. It is still making stars at a slow and steady rate, and it has enough material left to keep doing so for a very long time. It was never robbed of anything. It was never absorbed. It simply carried on, undisturbed at its own pace, for 13 billion years. From one angle, that is the most isolated existence in the universe. From another, it is the most peaceful one available. No collisions, no stripping, no mergers, nothing arriving to take anything away. If a galaxy could choose, it is genuinely unclear which it would pick. Solitude out here does not appear to be a punishment. It looks a great deal more like being left in peace. Take a quiet moment to reflect on what this means, astronaut. There is something in these galaxies that feels familiar, and it is worth sitting with for a moment. We tend to think of being alone as something that has gone wrong, a state to be fixed. But the void galaxies are not broken. They are not damaged versions of ordinary galaxies. They are simply galaxies that grew up somewhere quiet and became what that quiet allowed them to become. They kept what they had. They developed slowly. They were never pulled apart by anything. And the universe, seen honestly, is mostly like them. Emptiness is not the strange case out here. 80% of everything is void. The crowded, bright, colliding regions that fill our textbooks and our photographs are the unusual places. Thin, bright threads lace through an overwhelming dark. We happen to have grown up on one of those threads. Our sky is full of neighbors, And we learned nearly everything we know because they were close enough to see. Somewhere out there tonight, a spiral galaxy is turning slowly in a darkness we can barely imagine, making new stars with nothing around it for hundreds of millions of light years. It has been doing that peacefully for longer than Earth has existed. And it will still be doing it long after tonight is forgotten. We drift homeward now, back across the empty spaces, back toward the crowded, luminous filament where we happen to live. The Milky Way appears ahead, turning as it always has, with Andromeda glowing softly beyond it, and the small companion galaxies scattered around us like lights in distant windows. It is worth noticing just for a moment how fortunate this arrangement is. We can see other galaxies. We were able to work out what they are. Almost everything we understand about the universe followed from that one piece of luck. But tonight, there is nothing to work out and nothing to look for. The voids will still be there tomorrow, growing quietly, exactly as they have for 13 billion years. Close your eyes now. Let the vast, patient emptiness settle around you like a blanket. It is not cold out there, and it is not sad. It is simply quiet, and quiet is a good place to rest. Mission complete, astronaut. The stars will wait for you. Good night.